All right, hi everyone. I'm Doug, and today we're going to be covering one of the problems in the Algorithm Design Manual by Stephen Skeena, and we're going to be looking at Chapter 5, number 23. So I'm just going to read the text of the problem. So your job is to arrange n ill-behaved children in a straight line facing front. You're given a list of m statements in the form I hate j. I and j being children that are distinct, as in not the same child. It doesn't say that, but let's just assume that because it will become relevant later. Anyway, if I hates j, then you do not want to put I somewhere behind j, because then I is capable of throwing something at j. And the book wants us to provide an algorithm that orders this line of children, or says that it's not possible, in O of m plus n time. Right, so the first thing we're going to do here, just like any problem, is we're going to model it or just play around with it and try to understand what exactly it's asking. Now, because this is in the graph traversal chapter of the book, we can probably assume that this has something to do with graphs. When we get later on and we actually have the solution, I'll explain how you could come to the conclusion that this is a graph problem without specifically knowing that it is a graph problem. So say, for example, you're asked it in an exam or in an interview, or you just come up with this problem yourself, like when you're doing your work or something. So it's just important that you understand how to solve the problem first, and then we can look at how you would, because if I explain that now, then it'll just give too many clues for exactly what the solution is. All right, so knowing that this is a graph problem, let's just play around with it a bit, see if we can model it in some way. So we have, what are the objects we have here? So we have our children, and we have our relationships, and that's all of the data that we're given. So let's just write out this as the data. Our unknown is, we want to know, is it either possible to create a line, or we want to know what that line is. So rather, we want to know, is it impossible to order these children in a line, or what is the line if it is possible? Okay, so, and then what else do we have? So we have conditions here. So, so what's the condition upon which this would be considered solved? So we need the line to be arranged in such a way where the children are never arranged, like the children in the line are never arranged in such a way where a child who hates someone in front of them is actually behind them. So if someone hates someone else, then the hater, should always be ahead of the hatee being the person receiving the hate. Okay, so I'm not going to write that out. That's good enough for now. So our data here are the children in relationships. Now, knowing that this is a graph problem, how can we model this in a way that makes sense and we can actually do something with it? So we kind of have two choices here, right? In a graph, we have our vertices and our edges. And we have two data points here, or two kind of like groups of data, the children and the relationships. So we could either make the children the vertices and the relationships the edges, or we could make the children the edges and the relationships the vertices. Now, edges naturally model relationships, and vertices naturally model more like concrete things, like a kind of tangible thing that is stuck there and then can be related to other things. So based on that, it would be really weird to model the children as the edges. It makes a lot more sense to model the relationships as the edges and the children as the vertices. So let's go ahead and do that and just play around with it a little bit. All right, so let's say we have, we're just going to start with a simple example. Now, whenever we're doing a problem like this, it's possible that the example that we come up with will either be insufficient to completely understand the problem, or it'll just it'll be too simple, or it'll be too complicated even, or we'll just pick an example that doesn't really advance our understanding of it. So let's just take a simple one, and if any of those things happen, then we'll just evolve and create a new example and play around with it a bit more. And these things will become a bit apparent as we're drawing this graph and playing around with it anyway. So let's just start and assume there's like 4 children. So we have Adam, Bobby, Carl, and David. All right. So and then let's say we know that. So this isn't the graph yet. This is just modeling the relationships in a very kind of tabulated, simple, straight to the point way. And then we'll model the graph after we have the tabulation. So let's say Adam hates everyone. So these are all hates. So he hates Bobby, and he hates Carl, and he hates David. He's not a good kid at all. Bobby hates Carl, and let's say Carl hates, okay, we can't, so David hates Carl as well. Okay. Now we have this simple tabulation here. What this describes is that Adam hates everyone else, Bobby just hates Carl, Carl doesn't hate anyone, and David just hates Carl. So now that we know that the children are vertices, let's draw the edges for these. So the edges will represent the connections of Adam hates Bobby, and the vertices will just represent each child. Now, we have another choice here, which I haven't covered yet, which is this a directed or undirected graph? Or are there any other constraints on it at all? So just thinking about this logically, when you have the choice between directed or undirected, it doesn't make sense in this case to have it be undirected, because if Adam hates Carl, which we know here, Carl doesn't necessarily hate Adam back. So if we just draw a connection between Adam to Carl, like this, then what this implies, by virtue of being undirected, is that they both hate each other. And that doesn't help us. So in this case, we basically are stuck with directed. So we draw it like that instead. All right, so let's go ahead and draw the graph for this. So, okay, so we've got Adam, Bobby, Carl, and David. All right, and now let's draw the relationships between them. So we know that Adam hates everyone, so there's our directed edge from Adam to Carl, and another directed edge from Adam to David, and another directed edge from Adam to Bobby. Good. And then we're just walking through this table here and drawing the relationship. So Bobby to Carl is like this, another edge back from Bobby to Carl, and then finally from David to Carl. Wow, everyone hates Carl. I just realized that. So Adam's a bad kid, and Carl's a good kid that everyone hates. This is us, the nerds in school. Anyways, so right now what do we do with this? So we have our graph representing our relationships. It looks kind of interesting, but okay, now what? So in a case like this, if you don't know what you're doing and you're just playing around with the data and you're not sure where to go, one of the next logical things you can do is just solve this and see, just don't try and do any kind of fancy algorithm. Just try and come up with a solution for this that will work. and we'll satisfy the problem without the time constraint, because we can probably fix the time constraint later. If once we completely understand the problem, something will make more sense. It might even jump out to us if we're lucky, but it'll at least make more sense. So let's come up with a solution for this now. All right, so remember the constraint, which I wrote up here, the condition was that a hater is always ahead of a hatee. So the children shouldn't be lined up. Basically, in this case, it would be Carl should be at the front, because Carl should be at the back, because if anyone is in front of him, everyone hates him, so they can all throw stuff at him. And then on the converse is also true. If Carl is in the back, then Adam should be in the front, because Adam hates everyone else. So, all right, so now that we know that, Adam should be in the front. So here's our solution. Remember, this solution is just for this one example. It's not a generalized one that actually answers the problem. So we have Adam. This is the front, by the way. And then we have that we know Carl needs to be at the back. Is that read? No, let's make that a bit bigger, just to be easier to read. And then Carl down here. Okay, and now we have two choices for Bobby and David. So, well, in this case, they don't care about each other. Yeah, there's no real. So can you see here that there's no real distinction between these? Because let's say we put Bobby here and David here. So David hates Carl. David hates Carl only, and Carl's behind him. And Bobby only hates Carl as well, and Carl's also behind him. And then if we flip this so that David is first, it's the same thing, because nobody hates Adam, and everyone who hates Carl, which is everyone, is already in front of him. So at this point, this is an acceptable solution. You could actually, it's not the interesting thing that you can see from here, though, is that there's no one unique solution. There could be multiple. Because in this case, we could have flipped Bobby and David and both been valid solutions. Okay, so by now, and this should be the back. Okay, so by now, you might be starting to see something we could do with this. So let's think about what algorithms we have available to us and what the overall objective here is. So our overall objective here is to, given a graph like this, come up with a solution like this. Now, we have, from the chapter notes, like the stuff that we read earlier, we have several possible solutions or possible algorithms that we can use to solve this. So remember, we're always trying to boil things down into such a way where we can just kind of apply something that we already know. When we're solving, or when we're proving something that's not necessarily true, you generally have to do a bit more of like intuitive mental leaps. But in the case of solving problems like this, what we're trying to do is model the problem in a way such that we can apply one of our prepackaged algorithms to it. So what algorithms do we have available? From the chapter, we have DFS, which is short for depth first search, but you should know that if you read the chapter. And what does that enable us to do? So we can see cycles, because whenever we hit a back edge, that means we hit a cycle. It also allows us to quickly find articulation vertices, so doing component analysis. We have BFS, which is good for finding distances. Now remember, according to the notes, and this is true in practice as well, BFS is best for any kind of like distance problem, because anytime you start from one spot in a BFS to another, you're going to find the like shortest distance to every single other vertex. So, but that doesn't really seem relevant here, because we don't care about distances. We just care about ordering. Now what else do we have? We have topological sort, which is a special case of DFS. And what does this do? It gives us an ordering of the vertices such that one vertex, a vertex with a edge, so given two vertices u and v, it orders those vertices and the entire graph in such a way where an edge pointing from u to v, if there's an edge pointing from u to v, then u will always go before v in the topological sort. So it provides us an ordering of the vertices such that you're basically moving towards the edges that are like directed. So you're moving from like edges of lower in degree to edges that are of higher out degree. Okay, so all right, and what else do we have? So that's pretty much it. That's pretty much all we have here. So, okay, let's see what here makes sense. So DFS finding cycles. Well, from what we've seen here, at least so far, just keeping this example in mind, so knowing about cycles doesn't seem too important. So anytime we like throw any of these things away, we're not going to say, okay, this is definitely, anytime we throw away any of these algorithms, we're not going to say necessarily that these are useless and that we're not going to come back to them. But for now, we can cross out cycles. Okay. Component analysis, well, that doesn't seem too useful either, because we have one component here. And anytime we need to solve this problem, we could have one component, we could have many. So there might be something there, but it doesn't seem too useful right now. So we'll cross that out too. BFS and distances, well, that doesn't help either. The distances here are all, like from one child to another, it's just one. There doesn't seem to be any relation between distance and the ordering. So we'll cross that out too, and BFS in general. But topological sort, this one's interesting. So what does topological sort do? Well, given a graph, it gives us a ordering of those vertices. What do we have here? Oh, and one other constraint here is it only works on DAGs, so directed acyclical graph. We'll get to that in a moment, though. So let's just forget about the DAG for now. Let's just focus on the ordering of the vertices. So a topological sort will, given a graph, give us an ordering of vertices. Does that seem similar to what we're doing? Yes, it does. So the constraint it imposes, though, is that the graph is directed, which we have. It's acyclic. Ooh, we haven't talked about that yet, but we'll get back to that. Let's just assume that this graph is acyclic, so let's just assume this is valid for now, and it has to be a graph. So topological sort looks like what we're kind of looking for here. Okay, so this is a start. Now, let's just do a topological sort on this graph and see if it makes sense. So if we're going to topologically sort this, so I'm just going to run through the actual topological sort algorithm on this example, and we'll see what happens. So the algorithm starts at any vertex in the graph. So let's say we start at David. Actually, let's make it tough. Okay, Carl's first. So Carl. But then Carl has no out edges. So we stop there and just resume the Oh, by the way, a topological sort is, like I said, a specialization of the DFS. So if we're going to do a DFS exploration of a graph and it's not rooted, or even if it is and you just want to explore the whole thing, then once we've stopped at Karl or any vertex that has no edges out toward an unexplored vertex, then we just start over from another vertex. So we'll start from, let's say, David. Actually, no, that's not. Let's do Adam next. Okay, so we'd start from Adam, and then because this is a DFS, we're not going to actually process Adam yet. We're going to explore his edges. So we'll explore, it sounded kind of bad, we'll explore the edges of the relationships away from Adam to everyone else. So we explore to Karl, and Karl's already been visited, so we ignore that. So I'll just put this little X here for visited. Then Adam to David. So now we've explored David, and we've explored the edge toward David. And then from David, again, because DFS, we're not going to actually handle or process David yet. We'll explore the edge out to Karl. Karl's already been visited, so we go back to David, and now we write David. Okay, and now David's been visited. Okay, and then Adam still has edges relationships pointing away from him. So next we're going to follow that last edge to Bobby. And so that'll take us to Bobby, and then DFS will keep going to Karl. Karl's already been visited, so now we have handled Bobby, or we come back to Bobby, and then we've visited him. And then now there's nowhere to go from Bobby, so we go back to Adam. And there's no more edges connecting away from Adam, so we just process Adam at this point. Oh, okay. So you see this now? Well, this is once we flip this, so we'd have to, topological sort gives us the ordering of the vertices in reverse order. So we'd have to flip this before we could consider it topologically sorted. So I'll just do that now. So Adam's first, and then Karl's at the end. And then Bobby and David should be flipped. This part doesn't really matter because the way we got to Bobby and David was by just exploring in whatever order from Adam. So David, and then Bobby. Okay, so now that's our actual topological sort. All right, So this looks like basically exactly what we're looking for, and it makes sense intuitively too, right? Because one of the classic examples of the use cases for topological sort is in graphing dependency trees, or in resolving dependency for like jobs and stuff like that, job scheduling and dependencies. And in a way, this is a form of dependency, right? Because David is depending on being ahead of Karl, and Adam is depending on being ahead of everyone else. So it flows very naturally to think of this as a topological sort. Okay, so the one thing that we haven't covered yet is, which I said we'll get back to, is the acyclic part of the directed acyclic graph. So in this case, we were acyclic, but what happens if we have a cycle here? Well, let's add one and find out. So, I mean, we already know, of course, that topological sort can't handle cycles. But let's just model it to see what's happening. So we're not going to do the topological sort itself. We're just going to see what happens when we make the graph cyclic. So what's something here that would add a cycle? Well, there's several things. We could just add a back edge anywhere. So Carl goes back to Adam, Bobby goes back to Adam, David goes back to Adam, Carl goes back to Bobby. Any of those would work. We could also create a triangle. So can we? No, there's no triangles I see here except for a back edge from Carl to Adam. Yeah, so let's just add a back edge somewhere. So Carl also hates Adam, let's say. All right, so we can't topologically sort this because one of the constraints on topological sort is that the graph being fed into it is acyclic, and that's okay. So, but let's just see what happens to the problem when we do that. So if we try to solve this ourselves just by hand, remember before we had Adam at the front, Carl at the back, and then either Bobby or David in the middle in whatever order. But in this case, there's no way, if we draw Adam here and Carl here, now Carl and Adam hate each other. So Carl can now throw something at Adam, but if we put Adam here, and Carl here, well, Adam can still throw something at Carl. So, and then going back to the problem statement itself, we wanted to know if it is possible or not to give an algorithm that orders this line. Now, it doesn't necessarily mean that it's only possible in one case. It could mean possible in general. But in this case, we want to know for each example given to us or each situation provided, is it possible or not to order the line? And in this case, it is not, because we can't put these two in such a way where one of them can't throw something at the other. So what we've gotten here is, for free, the topological sort has given us for free the constraint that is requested as part of the question statement that is it possible or not to order this line. So if we find that there is a cycle in the graph that we are given, we can just say straight away, no, there is no way. There's no way to order this line. Okay, so it looks like we've more or less solved this now. So this example was pretty good because it showed us most of the qualities that we're looking for. We got to, we explored all of the possible algorithms that are like, I guess you could see them as being analogous to the problem. So we modeled the problem, and then we looked for analogous pre-formulated algorithms that can be used as solutions. We arrived at topological sort, which generates exactly what we're looking for here. And then we also got another part of the problem statement for free, which is the acyclic ordering. Now, last thing is, well, second last thing is, what is the runtime of this? Well, topological sort is O of V plus E. So, well, that's not readable. Well, anyway, that says, I'll write it over here instead. So, O of V plus E. Could even be theta, but whatever. And again, looking at the problem solution, we wanted O of M plus N, where M is the number of edges and N is the number of vertices, or M is the number of relationships and N is the number of children. So this is exactly what we wanted as well, too. Okay, so the last thing left to do is to just verify that this is correct. Now, how can we do that? Well, we have this one example. Now, can we think of any counterexamples of where this wouldn't work? Well, let's just start thinking of examples, like weird ones. So we already covered the base case with an acyclic graph, and we covered the case with a cyclic graph, and we found that the cyclic graph was handled for free for us by the topological sort constraint. So let's just model this another way. So let's say there's Adam, what did I call him, Bobby, Carl, and David, and none of them has any relationship to each other. Well, how do we topologically sort this? Easy. We just go through each vertex. We see that there's no edges connecting away from it, and then we print them in any order. So any permutation of these 4 vertices in a list is a valid solution because none of them hates each other, so they can be in any order. So we could have Adam, Carl, Bobby, David. Or we could swap these two, or we could swap these two. It doesn't matter. These are all valid solutions. Okay, so topological sort handles that correctly. What's another example? Ooh, let's try a path. Okay, so Adam hates Bobby, who hates Carl, who hates David. So this is just a path. Now, how will the topological sort handle this? Well, it depends on the start vertex, but basically what will happen is, let's say we start at Carl. So we'll DFS from Carl to David. So we'll get, and then David's the final step. So David will be first, because remember, DFS processes vertices deepest first, given the name DFS. So David will be first, and then we'll go back to Carl once David's been visited. Then we'll have, there's no edges out from Carl after that, so we process Carl. Okay, and then we'll start from another vertex, let's say Adam. So from Adam, we DFS to Bobby. And Bobby explores to I jumped ahead a bit here. So Bobby DFSs to Carl, but Carl's already been visited, so we just handle Bobby, and then we go back to Adam again. And there's no more edges from Adam, so we visit him and record him. And then remember, topological sort has to be flipped, so it would actually be Adam, Bobby, Carl, David. And is that right? Well, let's see. Okay, so Adam hates Bobby, but Adam is ahead of Bobby. Bobby hates Carl, but Bobby is ahead of Carl. Carl hates David, but Carl is ahead of David. Looks right to me. All right. So we could probably come up with some kind of other... Let's just do one more example here of 2 components, because I alluded to this before, but we didn't really talk about it. So let's say we have Evan and Francis. And Evan hates Francis. So this is still all one graph. So we could just continue the DFS that we just did here. So if we go to... Actually, you know what? Let's start it over, just to make this abundantly clear. All right, so we're going to do our topological sort of this graph again with the 2 components, with Evan, Francis, Adam, Bobby, Carl, and David. All right, so let's say we start at Francis. So Francis has no edges connecting away, so Francis is first. Then let's say we go to Carl. No, let's say we go to Bobby. So DFS, we're at David. Okay, David's been visited. Then Carl, because of backtracking. Then to Bobby, because of backtracking. Okay, and now we have 2 options of vertices left to start from. let's say we start from Evan, so we put Evan, and we explore out. Francis has already been visited, so then the last one is Adam. Okay, and now rearranging this, because remember this is flipped. Topological sort, it gives us in reverse order. So Adam would be first, and then Evan, and then Bobby, and then Carl, and then David, and then Francis. Okay. Now let's see, is that correct? So Adam's first. Adam hates only Bobby. Adam is ahead of Bobby, so that's valid. Evan is next. Evan hates Francis, but Evan is ahead of Francis, so that's valid. Bobby hates Carl, but Bobby is ahead of Carl, so that's valid. Carl hates David, but Carl is ahead of David, so that's valid. And Francis doesn't hate anyone, so he can be, well, there's no constraints on him. Okay, so this seems to solve the problem correctly for every case that we've come up with here. Now, it might be possible that with like a bigger graph or something, there may be some case that we didn't think of here, but this covers the basic series of possibilities that we can have with a relatively small amount of vertices. So at this point, we could pretty confidently say that we've solved this. Of course, you could go into like deeper mathematical proofs and stuff, but this is like good enough generally for at least like checking your solution with the book. Okay, and then the last thing, which I think is really important, is if you weren't in the graph theory or graph traversal section of the textbook, how would you know that that the way to solve this is with a graph? Well, there are several cues here. So the first one is, well, I don't know if this is fair because you might not necessarily get this. You might not necessarily get this additional information in real life. And what I'm referring to is the O of m plus n constraint on time complexity. So in real life, you definitely wouldn't have that. You would just know that it has to be fast. In an exam, they might write that, maybe not. So if you see something like that where it's talking about edges and vertices, like of course that's going to tell you that it's some kind of graph problem. But if you don't see that, the more important thing actually is the Hates relationships. So anytime you're seeing a relationship between different, like the data source within the problem, whether that's jobs or scheduling or children or whatever else, if there's a relationship between them, that should be a cue right away that there is some kind of graph problem there. And then even more specifically is we want this like Hates relationship. So when it explains it as like I hates J, then that should immediately cue us to think, okay, there's some kind of directed component to this. And again, if we think of like something being directed, then that is another that's another point for it being a graph problem, because there aren't many other like elementary CS concepts that encapsulate this idea of directing something between data sources. And then the last thing is right, we want the ordering of this line. So that doesn't necessarily scream graph theory. It cues at it or hints at it, but it doesn't scream it. What that tells us is that there's some kind of topological sorting, because what it's asking for here is a sorting of the vertices or sorting of the data. But it's not simple, because you can't just say, like, you can't, in this case, say Adam is greater than Bobby or David is greater than Carl. Like, it might make sense in this example just because of the way we formulated it, but in the previous example, the first one we worked with, where there's many different relationships between the children, that didn't make sense. So that's a point for it not being a like traditional sorting problem. So you wouldn't be able to like quick sort it or something like that. And topological sort is one of the only things that one of the only algorithms that we have available, at least again in elementary, like kind of intro to CS sort of material for ordering data in a graph. So yeah, so to conclude, we walked through modeling this in a useful way using graphs by representing children as vertices and the edges between them directed, representing the hate relationships. We walked through all the algorithms that we had available for like solving a graph problem once it's been modeled. So DFS, BFS, topological sort. There are others, but they just didn't really seem applicable. We scratched out DFS, at least in the unspecialized format, and all of BFS. And we said, okay, topological sort makes the most sense here. We walked through all of the possible, not all of the possible graphs, but several different types without getting into like really complicated, large amount of vertices graphs. Then we verified the solution using additional examples such as this one. And then we walked through how you would know that this is a graph problem and a topological sorting problem without seeing it, without it being explicitly told to you. And that's pretty much it. So hope you enjoyed that. If you have any questions, leave a comment. Yeah, thanks.